of the textbook, so try not to be too impressed. In AP Chem, there's 5 different solutions that you have to be aware that those are solutions. So you can have a solution that is a gas dissolved in a gas, which is like air. Okay, air is around 70% nitrogen, if not a little bit more than that, which means that that would probably be considered the solvent. And then the solutes are oxygen and carbon dioxide and methane and argon and all the other stuff. The liquid solutions, you can have a gas dissolved in liquid, like with soda. You can have a liquid dissolved in liquid, which is how drinking alcohol is formed. And you can have a solid dissolved in liquid, like salt water. Okay, and then the 5th kind is a solid dissolved with a solid, which I know sounds counterintuitive because obviously 2 solids can't really mix together like that. But alloys are just made by first melting them down and then letting them reform after they've mixed together. So you get brass, bronze, stainless steel, all that kind of stuff. Okay, but why? Why do solutions form? Why does it happen? So pretty much for the most part in chemistry, whenever we talk about why something happens, it's usually energy related. Molecules have potential energy trapped inside of their bonds. If they go through a chemical reaction, usually the goal is to release potential energy so that they exist in a lower energy level state afterwards, which would be what an exothermic reaction is. But with solutions, there's no chemical change. So it's not really like the 2 substances mixing together have some kind of change in their potential energy. They're just essentially more disorganized than they used to be. For example, if we consider these 2 substances as 2 gases and the border between them is removed, we know that what they're going to do is mix together. And, part of that is because they're moving. So obviously, if they have more space to move around, that's what they're going to do. But scientists are not okay with just saying because things are moving. There has to be, a fancy word to explain why things happen. And the word that explains why something happens, even if it's not based on a potential energy change, is entropy, which is the randomization of matter and energy in the universe. So, at the very, very beginning, if you follow the Big Bang Theory, matter was hyper-organized in one tiny place, which means it had very low entropy, and then the Big Bang happened, and everything spewed out into the universe, and stars formed, and then they exploded, and they spewed more things out into the universe, and now the universe is expanding, and everything's just happening, and stuff's just turning into heat, which is super disorganized energy. And whatever, apparently that's just the way the universe works. So more entropy all the time. More chill examples of entropy would be like an ice cube is going to melt. Ice is very organized. Liquid water is a little bit more disorganized. So that is entropy in action. And there's reasons why it's happening. It's absorbing heat and blah, blah, blah. But essentially what we're saying is it goes from organized to disorganized. You can even look at an example like you can spend energy organizing your room, but it's always going to end up being disorganized eventually. The nature of the universe is unless you're constantly doing upkeep, the universe is going to end up in a disorganized state. So, if in doubt and you don't know how to explain why something's happening, entropy is always a good fallback, as my friend here from the History Channel, my favorite friend, the alien guy, he's emphasizing it here. Okay, so more fancy work of me taking pictures of the textbook. Intermolecular forces is also an explanation for why solutions form. It depends on whether or not the intermolecular forces are similar or not. So the reason why, say, like oil and water do not mix is because the intermolecular forces are too different. But the reason why alcohol and water will mix is because the intermolecular forces are very similar. So if we look at this chart, for example, okay, what has to happen is the interactions between the solute and the solvent have to be better or at least equal to the interactions that they were already getting when they were by themselves. So let's talk about like our water and salt as an example. Okay, so the solvent would be the water. We know that it has hydrogen bonding. So that would be like this, okay? And then salt is an ionic bond, so it's going to have ionic bonding as its intermolecular force. Okay, that's what the two things are separate. So we have hydrogen bonding and we have ions. Okay, when the two things are mixed together, we end up with what is called the ion dipole interaction because the sodium and the chlorine are going to separate. So we have ion dipole. Okay, that is a very strong solute-solvent interaction. So the interaction between water and the sodium and the chlorine is going to be greater than the interactions that they were experiencing when they were alone, which is the reason why it happens naturally. The second example is more like if we mixed alcohol and water. Okay, so water is obviously the quintessential example of hydrogen bonding. So water by itself, hydrogen bonding. But ethanol also experiences hydrogen bonding. So what we're saying here is the solvent has hydrogen bonding, the solute has hydrogen bonding, which means when they're mixed together, they're both going to have hydrogen bonding together, so they're equal to each other, which means yes, the solution will form. And the third example, okay, so this might be more like a oil and water situation. So if we go back to our chart here, we've got all of our different things going on. Let's say we were doing oil, water. So oil has dispersion forces, which are very weak, okay, and then water has hydrogen bonding. So when we're looking at this, we've got one that is super strong and one that is super weak. Okay, and what we know is that this interaction is too weak to break into the hydrogen bonding that's happening between water molecules. So the interaction between oil and water is so low that they are better off staying the way they are, which is the reason why the solution probably will not form. There is a little, relative disparity on here, because what that means is it depends on how big of a difference. So like oil and water are extremely different, which is the reason why they don't mix. But we've talked about like the solubility of solids. Some of them are extremely soluble, some of them are extremely insoluble, but there's a lot of solids that are actually kind of in between those two. And that's because their intermolecular forces are kind of close to they might make good ion dipole bonds. It depends. So it depends on how big is this difference of the solvent-solvent interactions versus solute-solute. The closer it is to the equal sign, the more likely it is that the solution will form anyway. On page 550, there's a very small table of a few examples of polar and non-polar solvents. So water, acetone, ethanol. I don't know why acetone is on the list because I've always considered that a non-polar solvent, but who am I? I probably just don't know what I'm talking about. The non-polar examples, if you, in college, if you decide that you're going to major in bio or chemistry or you're on some kind of medical track, you're going to probably take organic chem, which means that you'll use these non-polar solvents a lot. Hexane, ether, those are non-polar liquids, and then fat in your body is obviously non-polar, which is why it doesn't mix with water. So one thing that you're going to be expected to be able to do is if you look at a picture of a substance or you're told a name of a substance, you should be able to tell based on intermolecular forces if it's going to dissolve in water or not. So if we look at these vitamins and you're asked, is it going to be water soluble or is it going to be fat soluble? The reason why that matters is because, the reason why we have to know that period is we have to know, can you overdose on those substances? If they're water soluble, it means that they're going to dissolve in your system and they'll leave your body through urine. So you essentially cannot overdose on those. If they're fat soluble, it means they stay in your system for an extended period of time, which means you have to be more careful about how much of them you ingest. So if we're looking at vitamin C, we see hydroxide group, hydroxide group, hydroxide group, hydroxide group. There's oxygens all over the place. Okay, anytime you see hydrogens, oxygens, nitrogens, and fluorines, you've got to think polarity. So vitamin C is a superpolar molecule, definitely not symmetrical, which means that it's going to be water soluble. Okay, essentially you cannot overdose on vitamin C. You'd have to eat an insane amount. Vitamin K, we do have an oxygen here and here. Okay, this is carbon, 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 carbon. That's nonpolar. Anytime you see carbons, you have to think that that section of that molecule is nonpolar. So we do have some slight negativity where those oxygens are, but you also have to consider the fact that they are equal and opposite spaced from each other, which kind of decreases their polarity. So this would definitely be considered a fat-soluble molecule. All right, vitamin A, we've got all carbons over here. Okay, that is going to be a very large non-polar section. We do have one itty-bitty hydroxide, but this is such a large molecule, this is definitely going to be fat-soluble. And then the last one. Okay, here we have hydroxide, oxygen, nitrogen and hydrogen, hydroxide, hydroxide. The oxygen, there's another oxygen, they're not equal and opposite. Okay, this is definitely a polar molecule, which means it would be water soluble. Okay, one last example of, well, not really, there's two. Okay, this is the second to last. You might have to be able to answer a question like which of these could dissolve in hexane, which you need to remember that's non-polar. Probably you would have some kind of reference sheet to remember that. Water is definitely polar, which means it's not going to dissolve in a non-polar substance. Okay, hydrochloric acid, definitely polar. Okay, nitrogen and hydrogen, that forms a hydrogen bonding as long as the substance is a polar shape, which this is trigonal pyramidal, so definitely polar. Okay, we have got a long carbon chain. That means nonpolar, which means it would dissolve in a nonpolar substance. And the last table that I'm going to explain. Okay, so this one's a little bit different. Okay, this one actually has recordings of how soluble they are in polar substances and in non-polar substances. So we've talked about this. Okay, this kind of goes back to this chart, which there's definitely an easier way to do this, but you know, why not do it the hard way? It's how we learn in life sometimes. Okay, so this goes back to this chart. Okay, is the interaction between the solvent and the solute high? Is it equal to what it would have been when they were separated, or is it starting to be like greater if they stay separated than when they're mixed together? So if we go back to this, okay, these are all alcohols, which means yes, they all have a polar section. Okay, right here where there's an oxygen, hydrogen, we have a small little bit of polarity. Okay, but what's coming into play here is how big is the non-polar side, because that changes the overall polarity of the molecule. So when we're looking at soluble in water, okay, this tiny little molecule right here, this non-polar section is itty-bitty, which means that the polarity is going to win out. This hydroxide right here makes it miscible with water, which means soluble. And what we see on this side, there's a number here suggesting that there's a limit to how many moles of that alcohol will dissolve in 100 grams of hexane. So there's a limit, which means it's not very soluble in a non-polar substance. So polar molecule dissolves in a polar substance, not very good at dissolving in a non-polar substance. Okay, makes sense. When we look at the next one, okay, now we've got an increased section of non-polarity. Okay, we still have the polarity of the hydroxide, which means it's still mixing with water, but now we also have a nonpolar section. So this is kind of like soap, where it's a little bit nonpolar and a little bit polar. So now it's miscible in both. Okay, we can dissolve it in water and we can dissolve it in hexane. When we go to the next one, we've got a similar situation. Okay, it's getting a little bit bigger, the nonpolar section's a little bit larger, but it's still not too large, which means that the hydroxide allows it to be miscible in water, but the larger carbon chain that propanol has also allows it to be dissolved in hexane. Okay, in the next one, we see the change. So now we have a very large nonpolar section, okay, and we still only have one hydroxide. So now the size of this nonpolar is making it, yes, it's definitely very soluble in a nonpolar substance, but now we have limits. It does not dissolve very well in water because there's just too much carbon chain for the water to keep track of. And then you can see with the pentanol, okay, there's an even bigger difference. So now we have a huge 5 carbon chain of nonpolar stuff with just this teeny bitty little hydroxide all by itself over there on the right, which means it's very, 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 very immiscible in water. Okay, and it's very good at dissolving in hexane.